I'm just going to free talk and record. So welcome, and this is just a brief introduction to the next bit, which is electrical potential and potential energy. So far we've talked about forces and fields. So we've talked about forces and we've talked about fields. And that is a bit like the gravitational force, which is the weight, and the gravitational field, which is little g. And little g was the force per kilogram, and the force was newtons. And over here, this was in newtons, and this one here was in newtons per coulomb. So these analogies are really useful. As part of this, the next thing we went to was potential energy. And we said, well, potential energy is caused by work. And we said we could find our potential energy, we called it UG, by saying, well, that's going to be our force times a distance, which equaled mg, which is our force times h. And you remember that? Okay, I'd like to talk about my electrostatic potential energy, which would be a force times a displacement, which would be like your n times a d, or an e, or an f, or an n times an x, or something, yeah? What we didn't talk about over here, because we didn't hop from planet to planet to planet. So if I tell you, oh, you're going to climb a 17,000 meter tall mountain today, you might say, that's impossible. But then I say, oh, it's on asteroid Bonaquisti. You go, oh, that's 2 steps. Because the gravity on asteroid Bonaquisti is so small that you can bound up, 1,000 kilometers in 1 step because its pull of gravity is so little. So in order to figure out how much energy you need to exert to do a job, you need to know the pull of gravity on that planet. And one of the ways of doing this is, let's talk about energy per kilogram. That would be kind of useful because you know the amount of kilograms you have. So I could have talked about my, not potential energy, but my potential. We never did. But let's say I talked about my potential, which would be my UG per kilogram. If you like, UG divided by mass. And I can talk about my electric potential, which is my electric potential energy divided by the charge, if you like, divided by Q. And that has units of volts. So you've been, and we can make a bit more complicated, we can talk about differences in potential energy, and we can talk about differences in electrical potential energy, and we can talk about differences in gravitational potential, and we can talk about differences in potential. So when you go to the store and you buy a 9-volt battery, 9-volt cell, what that tells you is you have 9 joules of kinetic energy per 1 coulomb, because it is joules per coulomb. A volt is a joule per coulomb. If you buy a 1.5 volt battery, you got 1.5 joules for every coulomb. So that's the game we're playing. We're going to talk about, we've talked about force and we've talked about field, and we're going to introduce talking about potential energy, and we're going to talk about talking about potential. So 2 new terms, but one of them's somewhat familiar. To make it a little bit more complicated, we're going to talk about potential energy, and we're going to talk about difference in potential energy, and we're going to talk about potential, and we're going to talk about difference in potential. Really just like we did in gravity. If you did gravity and you did MGH, after a little while you were awakened to the rude idea that this is actually not your potential energy. That's your difference in potential energy compared with wherever you start measuring H from. Remember that? And we actually resolved it by saying we don't know where the bottom of the universe is, so potential energy at this point is a negative number of joules. The potential difference between this point and that point, this is even more negative, so the potential difference is positive. So we introduced potential energy, talking about difference in potential energy, and the books tend to wash over that, which kind of leads us to some confusion. But we end up with 6 things we want to talk about. And they all look remarkably similar, and they all sound remarkably similar, and it's easy to get them confused. So you've got to put the terms down side by side. And then the other little wrinkle is that I can have questions to do with this where I'm inside a capacitor, where the electric fields are nice and uniform. Or I can talk about this where I am around point charges, where the electric fields are anything but uniform. So I have a set of these, if you like, for uniform fields, which are mathematically very simple. I have a set of these for non-uniform fields, which are mathematically more complicated. And the wrinkle is that the book introduces them using the point source charges and then generalizes to the uniform fields. And I'm trying to figure out if it's better to use the uniform fields and then take the special case of the point charges. So there's like, well, 2 different scenarios of looking at 6 different things. And it kind of comes together next time. So what I'd like you to do is try and get a head start. Look at the old video before next time. So can I ask you a question? Well, I won't ask a question because it means people displaying themselves. But I know, because some people have talked to me, that some people are looking ahead. And I'd like you to just continue doing that and give me some feedback on how much it is helping, because the more it is helping, the more I can convince other people to look ahead, then the better everybody will do. That's, you know, you've got to steal time from behind the lecture, in front of the lecture, to get ahead. So you've got to kind of do work before you really need to do it. But I just think it's much more efficient, so please have a look at that. We've got a lab, and we're going to do electric fields in the lab, so I'll see you guys in the lab. And I'll see you guys later.